Yes, class. Now in the last class, we had started with mechanical properties of solids. So let's start with the class. In the last class, we had seen elasticity. Elasticity meant what? Means when the force was removed, any type of force was removed, the body was able to regain its property. Now, these type of forces that produce any conformational changes, these are known as deforming forces. And once the deforming forces are removed, and if the body is able to return to its original shape and size, then the body is known as elastic body. If it is not able to regain its exact original shape and size, then we say that is a plastic body. So three types of solid deformations are there: length changes, volume changes, and there's a change in shape. Based on that, as I've told, we have two quantities, stress and strain. First, let us discuss stress. Easy topic to be discussed. See, stress is the internal restoring force per unit area acting. And see, just understand first with the help of diagram. Suppose let's take that same example. Here I am having an iron rod over here. Fine. This is an iron rod. Now the cross-sectional area is A. Now I have applied some deforming force on this. And because of this, let's say some changes are produced. Let's say it has increased, the length. So this force, this deforming force per unit area, this is known as stress. Stress is basically deforming force per unit area. Force per unit area. Fine. So see, it's a scalar quantity. It's exactly similar to pressure. So force per unit area we write for pressure, thrust per unit area. That is the perpendicular force. Here the force is deforming force, and the cross-sectional area or whatever is the area, that is known as stress. So SI unit of force is Newton. SI unit of area is meter square. So 1 Newton meter square, right? Or straight away write the SI unit of pressure. Does anybody remember the SI unit of pressure? Pressure's SI unit. What is 1 Newton per meter equal to? It is equal to Pascal, denoted by P. So if you want, you can write the proper dimensional formula or also of this. mLt to the power minus 2 divided by L square. So this L will get cancelled. So mL to the power minus 1, T to the power minus 2. This is what is meant by stress. Now see, what did we see? Deforming forces produce not only one type of deformation. There's a change in length, there's a change in volume, there's a change in shape. So if normal stress is applied, see, three types of stresses will also be there. Three types of deformations were there. So first is known as normal stress, or it is also known as longitudinal stress. Two names, both the names are same, normal stress or longitudinal stress. So what is meant by this? If deforming force is applied perpendicularly, let's say this was the edge, this was the end of the wire, and here the force was applied like this, means making an angle of 90 degree over here. So this is known as longitudinal stress. Longitudinal stress. It is also force upon area only. Here just force is perpendicular 90 degree. And SI unit will also be pascals because it's a type of stress. But these are also of two types. If because of this perpendicular force, there is an increment in the length, we call it as tensile stress. And if somehow it is decreasing, let's say an opposite direction force is applied, something else, length is decreasing, then we say it is compressive stress. Fine, I'll repeat it. Let me just discuss rest of the type of stresses with you. Second is tangential stress. Remember in the last class when we just were about to end the class, I told you that deforming force is applied parallel to the surface. There's a change in shape. So if the deforming force is applied parallel, like the book, very thick books that you have, especially your class 11th reference books, if you put pressure on the upper part of the book, upper part will just sway a little bit and the lower portion will stay as it is, right? So this is tangential stress when force is applied parallel to the body. Perpendicular force, longitudinal stress or normal stress. Parallel force, tangential stress. So it brings out the change in the shape. And lastly, which we have is the volumetric stress. In volumetric stress class, see what will happen. Suppose this is a body. And now I have applied forces, perpendicular forces, be it perpendicular forces, normal forces on the surface like this 90 degree, making an angle of 90 degree on its surface. Fine. I have applied the forces on its surface. Now, obviously, because of force, what will happen? It will get compressed, right? And surface area was also something. So this force that was applied to the area is known as volumetric stress. So if the deforming force is applied perpendicularly on the body, which changes its volume, see, if force is applied perpendicularly, it could have been longitudinal or normal stress. But if the force that is applied perpendicular, it does not bring changes in length. It directly brings out changes in the volume. Then we say it is volumic strength. Now stress. Now I am repeating all the types of stresses. Class, anywhere you are having difficulty, any doubt, just stop me in there between. Fine. Stress is what? Stress is whatever is the deforming force that is applied divided by area. Deforming force per unit area. Normal stress. Normal stress or longitudinal stress was deforming force was perpendicular. The type of deforming force that decides the type of change determines your type of stress, right? So last time I'm again repeating, wherever you get stuck, stop me in there. Fine. Now see, normal stress or longitudinal stress was deforming force was applied perpendicularly. So that force per unit area became longitudinal stress. We also call it normal stress, but the usual common term is longitudinal stress. There are also of two types. If the force elongates a body or increases the length of the body, then the stress setup is called tensile stress. And if somehow it manages to decrease the length of the body, the stress setup is known as compressive stress. So tensile stress or compressive stress are just two types of longitudinal stresses only. Then we have tangential stress. Tangential stress was parallel force. Perpendicular force with change in length is longitudinal stress. Just per parallel forces, tangential. And perpendicular plus change in volume was volumetric stress. Perpendicular plus change in volume. Fine, note down stress. Any doubt you have from stress, please ask me. So stress is clear. Stress is exactly like pressure. Force per unit area, whatever force has been applied, that force here for, why is stress unique? Why is stress not named as stress? It's just the difference is that stress you have deforming force. The force should produce a change. Pressure can be anywhere. You have applied pressures also where no change is observed. That is known as stress. That is known as pressure. But in case of stress, you have specifically applied pressure. Now coming to strain. Strain is whatever is the change. See, three types of changes we had studied: change in shape, change in volume, change in length. So whatever is the change that has occurred, divided by the original change, whatever it was. Like, let's talk about length. Whatever change in length has been observed, divided by whatever was the original length. This is known as strain. So stress was force per unit area, strain is change in dimension by original dimension. Now see, since the types of dimensions are different, types of dimensions which are changing are different, so types of strains will also be different. So strains, firstly, if there's a change in length, just the length is changing. Let's say same example, if I give you that wire, we consider, let's say this is a wire, length is some L. Now this has elongated. So this much is extra part, delta L, let's say this is the change that has occurred. Or let's just write it as some L dash only. Let's write the complete length as now L dash. This complete length is L dash. So what is the change? Change will be L minus L, L dash minus L. This part that is coming extra, this is the change. Otherwise, both would have been the same. Let's say this change in length is delta L. So longitudinal strain will be change in length. So delta L, this is the change in length by original length L. And class, strain will always be unitless. See, whatever dimension you have above, same dimension you have in the denominator. So when you talk about SI units, no SI unit. It is unitless as well as dimensionless. Fine. So longitudinal strain means change in length. If it is only change in volume, so volumetric strain, change in volume by the original volume. So if, let's say, all these forces have compressed this body and this body has reached this point, right? The body is reaching this point, these red dotted lines. So the change is this perpendicular change. This you will be able to observe. This is the change that is coming, delta V. So change in volume, delta V by V. This will also be unitless. See, meter cube above, meter cube below, unitless. This is known as volumetric strain. And shearing stresses, see, shearing stresses, whatever change, see, it produces change in shape. So when deforming force produces a change in shape, that type of strain is known as shearing strain. How will you calculate it? See, let's say this force is applied and point B was the initial point. Now the point is C. The book, the way I give you the example of the book or anything that is heavy but not fixed, which can be slid away. So upper layers slide away while the lower layers stick to their original position only. Right, if they stick to their original position only. So C class, if you look at this triangle, the change in the length that will occur will be this only. Let's say this is delta L. And here this was the original length. If you look at this triangle, let me write it. This is theta, this is L, this is delta L. If you look, this is point A, this is point B, this is point C. I have just inverted the triangle for better calculations. If I write tan theta, that will be perpendicular by base. So perpendicular is BC by base BA. What is BC from the figure? Look and tell me. What is BC from the figure? Yes, class. If you look, right, tan theta, BC is, look at the figure, no, look at this triangle. Are you people listening? Or should I again call the names then?
Yes, ma'am.
Look at this. Just look at the triangle. What is BC? Yes, at least Waziha has tried. Not just L Waziha, Delta L. Good, at least you are alert in the class. So only Safura also responded to one thing and now answer was given by Waziha. See, L is BA Waziha. This is L. This is BC. That is delta L. So this will be delta L by L. And see, for small angle approximation, because you can also note here, the angle that it will be tilted by will be very small. So tan theta can approximately be written as theta. So shearing strain is delta L by L, which is represented by theta. Here your theta is the shearing strain. Fine, strain produced is called shearing strain. So three types of strains. I'm again repeating it. Strain is any change in dimension by the original dimension. Change in length, so by original length. Change in volume by original volume. Change in shape by original shape. Fine. These are known as, this is known as strain, sorry. Now, because we know there are different types of deformations that are occurring, three types of deformations are there. So three types of strains will also be there. We had three types of stresses, so three types of strains. So longitudinal strain is when there's a change in length to the original length. When there's a change in volume by original volume, we say it is volumetric strain, and change in the shape produced, that is also written as delta L by L only. Change in the length. This is known as shearing strain. But how to differentiate between shearing strain and longitudinal? In shearing strain, there's a change of shape. In longitudinal strain, length only changes. Shape does not get affected. Note it down, class. Any doubts you have, get it cleared. Now class, you have Hooke's law. Hooke's law is very easy. This lesson is very easy in comparison to other lessons. See, there's an elastic limit of every body. Elastic limit means there's a maximum stress that is applied, after which if that limit is crossed, no, then the body will not be able to recover its original state. Whatever, let's say chain length, there's a change in length. So if the elastic limit of that particular pipe or rod is crossed, that elastic limit is crossed, now it will remain elongated only. The original length will not be reached. So that limit, minimum criteria, after which when you remove the deforming force, the elasticity is not regained. That is known as elastic limit. So if that elastic limit is not exceeded, then class C, the stress is always directly proportional to strain. Or you can say, let's say this was the rod, here force was applied. This was the change in length. Let's say the change is this much, you can notice. Let's say this is delta x, change. So force is always proportional to this extension. The deforming force is always proportional to this extension. So it says that if this elastic limit is not exceeded, provided that the elastic limit is not exceeded, the stress is directly proportional to the strain. Stress is directly proportional to the strain. So it means we have to bring up a constant. Stress, let's say this constant is, put some K. So divided, stress by strain is equal to a constant, which we say, let me write it as E. This constant is known as modulus of elasticity. Modulus of elasticity. This constant, stress by strain, is known as modulus of elasticity. Now class, C, stress is directly proportional to strain only when the elastic limit is not exceeded. Fine. If I plot the graph between stress and strain, see, it will be a linearly proportional graph. If you calculate tan theta, that is the slope of graph, it will be directly stress by strain, and slope of the graph will be, stress by strain is what? Modulus of elasticity. But if you plot a graph that is strain versus stress, so strain by stress will be 1 by tan theta, which will be 1 by E. So slope will be 1 by bulk modulus. So stress by strain will be directly bulk modulus, and strain by stress will be inverse of it. Now see class, we know that there's not a single type of stress, not a single type of strain, 3 types of modifications and deformations also we had seen. So if these are different, so how will we have a single type of modulus? If there's a change in, let's say, longitudinal strain is there, you have volumetric stress, what type of stress, what type of strain, how will we determine that we have a single modulus of elasticity? So there are 3 types of moduli of elasticity. Young's modulus of elasticity, bulk modulus of elasticity, modulus of rigidity, change in the shape. Change in shape is modulus of rigidity, change in volume is bulk modulus of elasticity, change in length is Young's modulus of elasticity. All these 3 we have to discuss. You will be getting separate questions on these also. Do not worry about that. We'll start with Young's modulus also. We'll try to start it today. And it's then very small topics will be left. So I'm again repeating. Hooke's law says if elastic limit is not exceeded, then force produced is directly proportional to extension, or you can say stress is directly proportional to strain. The constant which you obtain is known as Young's, it is known as modulus of elasticity, which is of 3 types. If there's a change in length, you say Young's modulus of elasticity. If there's a change in volume, you call it as bulk modulus of elasticity. And if there's a change in shape, you say modulus of rigidity. All right, class. Now the graphs are also very simple. Direct strain, stress versus strain. You'll get bulk modulus of elasticity as the slope. If it is strain versus stress, so 1 by modulus of elasticity. I hope I'm clear to all of you. Still, if you have any queries, when you are copying it down, whenever you are stuck in between, ask me again, I'll repeat it. This is an easy lesson. Please try to score a full score in this. Now class, the first type of modulus of elasticity, that is Young's modulus. So as I have told you, this is because of change in length. So it is ratio of stress and strain. Now the type of stress and the type of strain will determine your modulus of elasticity. So for Young's modulus, if I tell you that it is because of change in length. So stress, which is because of change in length, was normal stress. Remember longitudinal stress or normal stress? We had seen, no? Longitudinal stress. Longitudinal, you can say, or you can say normal stress. This was equal to force upon area, remember? And the type of strain that occurred because of change in length was longitudinal strain. So the formula of longitudinal strain was delta L by L. So if you put in the ratio of this Young's modulus, which is represented by capital Y, this will be force by area divided by delta L by L. So if you write it properly, it will be force into force by area delta L by L. This is known as Young's modulus of elasticity. Here, this is the force, this is the original length, this is change in length, and A is the area. And SI unit, C class, here SI unit will be, stress has SI unit as Pascal, and strain has no SI unit. So if you take the ratio, you will still be getting Pascals only. So SI unit will be 1 Newton per meter, or you can say 1 Pascals also. Both are correct. Note it down, then we'll see some numericals based on this. Note it down first. See here class, this says a composite wire of uniform diameter 3 millimeter consisting of copper wire of length 2.2 meter and steel wire of length 1.6 meter. This is stretched by under a load by 0.7 millimeters. You have to find this load. See, one thing that is mentioned to us that the change in length of both are given. Change in length of copper and change in length of steel. Both are given to us. Right. But individual length is not given. The individual separate length is not given. Now, see class, what we can do, delta LCU plus delta LS is 0.7 millimeters. We can write this because it is said that stretched completely. Together they are stretched by 0.7 millimeters. Now, Young's modulus is given. See, when you write Young's modulus of copper, it will be force by area. Area will be the same area of cross section because 3 millimeter is diameter. Delta L by L. So L and delta L will have difference because it will be of copper. Then steel, again F by L will be there. L of steel and L of delta L of steel. So length, original lengths are also given. Take their ratio. See, take the ratio. If you take the ratio, you will get Young's modulus of copper by Young's modulus of steel. LCU by delta LCU into A delta LS by F LS. FA gets cancelled. YCU is 1.1 into 10 to the power 11 by Y steel is 2 into 10 to the power 11. Length of copper, it is given as 2.2 meters. Change in copper. See, change in length of copper can be written as 0.7 minus delta LS, right? And then delta LS can be written as delta LS only. And length of steels, this is 1.6 meters. From this equation, you can find out delta L, right? And then you can put it in any of the equation to get the value of force. Because area is already there, pi r square is the area. Understood? Note it down, see whatever answer you're getting. Then any doubts are there, I'll help you. Okay, class if completed. I'll stop here. Now in the next class, this lesson will be over. All right. So I'll complete the rest of the portion in the next class. If by chance, if we have class on Friday, I'll inform you if the other class is not there. If that other class will be there, then I'll share the videos. Otherwise, I'll have a class. Class, tell me one thing. Which lesson is the most difficult you're finding for the backup? That I'll complete on Friday. Out of all the lessons, 5 lessons have been missed by all of you, no? So projectile motion, projectile motion and dimension analysis. These are very small. See the video lectures of these. But from motion in a straight line, laws of motion, and initial of work energy in power. Let me know if you are having difficulty in any of the lessons. If it's fine, then you can see the videos. Otherwise, please let me know. All right, class. Okay, thank you so much.